Hello and welcome to today's lecture. Today we're going to be discussing Chapter 3, Data Input and Output. Specifically, we're going to be talking about strings and annotated output, so creating strings, converting numerical values to strings. We're also going to be discussing how you can enter data with the input function, inputting, outputting data files using cell arrays, and then also inputting Microsoft Excel files into MATLAB. So objectives for this chapter, we're going to present various means for displaying annotated numerical results in the MATLAB command window, as well as storing and retrieving data directly from files. We're also going to be introducing you to cell arrays. So we'll get started here with just some of the basics in regards to strings, or some of the literals. Strings are collections of any combination of letters, numbers, and special characters. They can be created, stored, and manipulated in arrays and are defined similar to that as vectors and matrices. They differ from an array of numerical values in that each character occupies one element in an array. It's defined by enclosing all of its characters between a pair of single quotation marks, as you see here. When you have created a string inside of those single quotation marks in MATLAB, it's going to turn that purple color that you see. They're typically used for displaying information to the command window, annotating data displayed to the command window, and annotating graphs. Here's a couple of examples for you for creating strings. So we're just going to show you how to do it because that's the easiest way to learn these. So let's just start with this example here. Let's say that we wanted to create a string testing 1, 2, 3. There's two different methods that you can use. This first method here just uses the single quotation marks, and the second method uses the square brackets. Either one of those are acceptable. It's a matter of preference, or it can be for your application. For example, if you wanted to transpose the string, then you would use the square brackets, obviously. Remember the subscript notation that we discussed from Chapter 2 with matrices and vectors? We can access elements of these strings or a group of characters from strings by using that subscript notation again. So for example, in the testing 1, 2, 3, if we wanted to access the letter G, we could use the S and then subscript 7 notation. Or if we wanted to access a group of the characters, such as the STIN, then we could use this S3 to 6 notation. Strings can also be concatenated, which basically just means you add them together to form a longer string. So let's say that we wanted to create a 1 by 20 string. We're going to do that by doing testing 1, 2, 3, comma, testing 1, 2, 3, and that will produce the 1 by 20 string. The 1 by 20 string for us by concatenating those together. We'll just continue here. So let's say that now we wanted to create a 2 by 10 matrix. So this time we have 2 rows and what's considered to be 10 columns, each character representing a column. We would do that this time using this semicolon here in between the two. Remember, that's what's used in matrices to create a new row. So then when you execute the script, you can see now we have 2 rows that are each comprised of the testing 1, 2, 3 string. And if we wanted to access the entire row, for example, we would still use this same notation like we did with the matrices and vectors, and this here would access all of the elements in row 1. This here would access all of row 2. So yeah, that would result in the complete testing 1, 2, 3 in both strings. You can find the starting location of strings within a string by using this function here, find string, so find str, and then you can list the strings here. So it searches for the longer of the 2 strings for the occurrences of the shorter of the two strings. So what does that mean? Let's look at an example here. Let's say that we want to find the occurrence of 1, 2, 3 and that concatenated string that we just did previously. So we use this here. So we defined SC is our concatenated string, so it has the 2 here. And then the location is equal to find string of our variable for our concatenated string, and then what it is specifically out of that string that we're looking for. So in this case, the 1, 2, 3, you do need to still use those single quotation marks. So when you execute it, it's going to tell you that SC is equal to testing 1, 2, 3, testing 1, 2, 3, and it's telling you that starting at location 8 and starting at location 18 is where 1, 2, 3 and 1, 2, 3 begin. If we place a string in each row of a matrix, we have a convenient way in which we can access string expressions. So the requirement is that each row must contain the same number of characters. This can be met by employing blanks that can be used to pad the expression, the string, when the individual string are not the same length. So basically you can see here, like in this lab, first, last, and middle, we want them all to be the same length. So in this particular case, we have 1, 2, 3, 4, 5, 6 characters. Here we only have 4, but we padded it by adding 2 blank spaces here. And then in first name, we padded it with 1 blank space. So then when you go to access that element, you'll see this B here, and then the 2 B's here. That actually signifies blank space. That's what that means when you see that. So first B, again, B indicates that blank space that we added here. The padding is performed by the syntax char, or character is what that stands for. Thus, the above expression can be replaced by the easier to use expression lab equals char, first, last, middle. And so now when we do the size, we can see that this is a 3 by 6. So 3 by 6, that's our order here. And you can see that it automatically took care of those blank spaces for us. So again, this function here makes it easier so that you don't have to manually add those blank spaces. We can remove any trailing blanks from those outputs by using this deblank function here. We can also use string trim, and that can be used to remove the leading and trailing blanks. So deblank removes the trailing, string trim removes the leading and the trailing blanks from your string. So let's say, for example, that we want to, in this example here, we could do deblank lab, and that would remove those trailing ones, or we can do string trim, and if there were some below and some after, it would remove those for us. We can also compare strings. And so let's say that we have a string A and a string B. If it's true, meaning that they're the same size or the same order, then it will produce for us a 1. If it's false, meaning they're not the same, then it will produce 0. So let's say, for example, we wanted to see if the two words are the same in A and B. So look here. So we have A is equal to yes and no, but you see how we have the 2 leading blanks and 2 trailing blanks. But in B, we only have 1 leading blank and 1 trailing blank. So we have C1 is equal to string compare A and B. But in C2, we've done string compare, but in this case, we use that string trim where it's removing those leading and trailing blanks from both A and B. And so when it executes, we can see where we just did the straight comparison where the blanks were left, it's false. And in this C2, where we trimmed the string, it's now true because A and B are the same. We do have the ability to convert numerical values to strings and to display those numerical values. So to convert a numerical value to a string, we use this num to string function here. Or there's also this notation. So num is just going to be your variable. It's a number, it's an array of numbers, or an expression resulting in a number. The n over here in the second notation, what that is the number of digits that you want to display. So if you leave that out, it's automatically going to default to n being equal to 5. So let's look at an example here. We have a is equal to 1,000 pi, which is equal to 3,141.59, yada yada. So then the various values of n will display the digits shown below. So you can see we've done a couple of different examples here. So you can see how changing the number of digits to be displayed affects it. So we have a is equal to this. If we just want to display 1, if we want to display 3, so you can see here 1, 2, 3. In this case, now we're displaying 1, 2, 3, 4, 5, and 8. So that's just a simple way that you can do that. Now, know though that the decimal point does not count as a digit when you are using the num to string. A typical construct is to use num to string to concatenate the converted numerical values with some identifying text. So let's say that num is weight in kilograms and it's to be identified as such. Then when we display that to the command window, we can use this notation here. So let's say we have num equals 12.567. We can use display and then product weight is equal to num to string num. So that's going to put this into here. And then now we can put this kilogram here. Again, those single quotation marks are required. And so when we execute the code, we can now see that it's going to spit out for us product weight equals the 12.567 kilograms. So now our numerical value has been annotated to the command window, which is really convenient. Another thing to notice here is there's this little blank space right here, and that was used to create a space between this number 7 and the K there, just for clarity. Of course, you don't have to do that, but you can. Another thing that's important to know is that one blank space is required on each side of num to string. So that's required right here and right here. If you try to execute the script and you did not have these blanks here and here, you would receive an error in the command window from MATLAB. Here's another example. So let's say that we wanted to display a vector of lengths of an object. So then we could use this script here. So now we have num, which is equal to this vector here. So we have the 3 different values. In this case, we're going to display object length, num to string. Again, notice we have a space before and after, and the length is in meters. So when we execute, now we have all 3 values that have displayed, and now we show that it's in meters. We do have the ability as well to convert an integer to a string. We just use that using the IntoString function. If num is not an integer, then it will be rounded to 1. So let's say, for example, we do IntoString of pi. It's automatically going to round that to an integer value. An alternative way to display the formatted data to the MATLAB command window is to use FPrintF. This is a really convenient function, one that you're probably going to use quite a bit. So we see this notation here. This is standard notation, so just be aware of that, and I'll explain what each of these here represents. So FPrintF is our function. This one here, it just indicates that the output goes to the command window. And most of the applications for this course, that's just going to be what you'll use. You'll use 1 there. This percent ... so we'll put some syntax there. I'll explain that in a minute. It does need to go in the single quotation marks, and then you'll have your variables. So again, the percent is the specific formatting that you want to use for the variables, and then percent precedes each format specification, which is of the form this x.yq. So what does that mean? We know that q specifies the format, x specifies the minimum number of digits to be displayed, and y is the number of digits to the right of the decimal point. So let's look at examples so we can see what all of this means. let's say that we have this vector here, so we have num is equal to these 4 elements, and we want to display them in one line to the command window, but we're going to use the FPrintF to do some formatting to these numbers. So you see down here we have FPrintF, so 1, again, that's just saying to display it to the command window. We have num, so that's our variable for this vector. And then this here is that formatting specification. So we have, again, the single quotes, the %, and then 5.2F. F is pretty much the standard formatting specification that you'll use in this course. If you want, you can do the help for FPrintF, and it'll let you know what the other options are, but typically just F is going to be the standard one that you're going to use. So then you can see this 0.2 here says to display 2 places after the decimal point, which you can see that we have. So that's all that. Here's another example here. This time, instead of displaying it as a row, we're going to display it as a column. And so the difference that you see here is this \n. And what that does is that creates a new row. It makes it move down to the next line. So basically it's going to take for each value of num, each element of num, it's going to put that on a new line, still using that same formatting specifications, minimum of 5 digits, and then the 2 places following the decimal point. To display each number with the appropriate number of digits, annotate each value, and print it to the column form, we can use this syntax here. So we have that same vector as before for num, but this time we have FPrintF 1, again, just displaying to the command window, and we're saying weight is equal to 2.0, so we're saying minimum of 2 digits, 0 decimal places, and so when you and then space kilograms, and then \n or /. So then you can see when we execute the code, now it's saying weight is equal to 12 space kilograms, and that's what this syntax here did. Next, we can do pressure equals 2.0, so again, minimum of 2 digits, 0 places after the decimal points, measured in kPa. So now we see pressure is equal to -14 kPa. And then it continues through. We did the same thing with time, only this time we did 3 places following the decimal point. And in this case for length, we did 5 places following the decimal point. But you can see now how it makes it really convenient when we're displaying information to the command window, and instead of just having it spit out 12, -14, and so on. Now we can say specifically, well, what do those numbers in that vector represent? So it makes it really convenient for readability so that others can understand what's going on in your code. Num2String can also employ the format specifications of FPrintF by replacing the second argument n in num2string with a string format specification. So suppose that we want to display a very small number as 0 instead of an exponent form. So we could do that. Let's say that we have x is equal to this 0.00045. We could do that by using our num2string. So then we have our variable x here, so that's going to be fed into right here. And then now we're saying minimum of 2 digits to 1 decimal point. So when it does that, it displays this 0.0 here. So again, we can use that syntax like we saw before with our num2string to specify the format that we want the output to display to the command window. Let's say that we wanted the user to be able to enter a numerical value. Let's say that we ask for a certain temperature in degrees Celsius. We can prompt the user in the command window to enter a value for that temperature. So we could do that using this input function here. So in this particular case, we did input data equals input, and then you use this string. Now your string can say whatever. In this case, it says enter temperature in degrees Celsius. The space here is just because when it displays the command window for readability, it has a space there. So what it would do is when you execute this code, this is what is going to show up in the command window. And then the user can enter in, for example, 121.7. And what that does is that goes and assigns 121.7 as the value for input data. And then you can continue to use input data in further code to do any additional manipulations or calculations, plotting of graphs, or whatever you want to do with that temperature. So this shows, for example, here how we could do that even in just a single line. So in this case, we said enter the starting angle in degrees. Let's say that we wanted to convert it from degrees to radians or radians to degrees, however you wanted to do it. So what you would do is you multiply by pi over 180 here. So then what it would display to the user is enter the starting angle in degrees. So the user could then enter, say, 45 degrees. And then what it's going to do is it's automatically going to convert that to radians for us by multiplying whatever's entered by pi over 180. And so that will display input data is equal to this 0.7854 radians. Let's say that we wanted the user to be able to input a string instead of just a numerical value. We can do that as well. So let's say in this particular case, we want the user to enter a file name, including its extension. What's particularly different here is that you need to use this syntax. So the comma, single quotation marks, and the S here. And what that's signifying to MATLAB is that a string is going to be entered by the user. So for example, this here is what it will display to the command window, and then the user could enter something like dataset3.txt. And what you'll notice here is that even though it's a string, the user didn't have to use single quotation marks, and that's because we used this syntax here, so that all they had to do was enter dataset3.txt. To input a vector of numerical values, we can do that as well. So let's say that we want temperature in degrees Celsius, but this time instead of a single value, we want 4 temperatures in degrees Celsius. So the user could enter that just by saying, enter 4 temperatures in degrees Celsius, and then they could use the square brackets to create this vector of 4 values for the temperatures. And so then when it's executed, then that is going to create a new vector for input, where input data will be equal to these values. And then again, you can do further computations on that. If a column vector was required, then the user would have to use this apostrophe notation here, that prime notation, to transpose it. And basically that would, again, take it from a row to a column. Or they would have to do the semicolon notation. So again, that would create the 4 separate rows here to create a column vector. If we wanted to create a matrix using the input function, that's also possible. Let's say that we want to enter 3 temperatures in degrees Celsius for levels 1 and 2. This is just an example out of your text, so feel free to go take a look to get the background and syntax if you want to. So here's what will be displayed to the command window, and then the user would enter, for example, this syntax here. So in this particular case, we've created a 2 by 3 array. So here is our semicolon. That's what started the second row. So 1 row, 2 row by 3 columns. So again, we can prompt the user to enter a string, a single scalar value, a vector, or a matrix. We do have the ability to load and save files with MATLAB. We'll start with how you load files. So a couple of things before we specifically go into how you do it. Loading reads the data on a row by row basis. So each row is separated by an enter, where enter is used instead of semicolon. Each data value is separated by either 1 or more blanks or a comma. The number of columns of data in each row must be the same. For a row vector, data is entered without using enter, and for a column vector, each data value is followed by an enter command. So assume that the data resides in the ASCII text file data section 33.txt, and this is the particular data inside of that text file. To load it, you would just do load, and then the name of your file. So this uses, again, the single quotation mark, so that is a string here, but that will load the file for you that contains this particular data set. Furthermore, we can load it and then we can do further manipulations with it. So let's say that we wanted to square all of the values within the matrix set from data section 33. We can do that by literally taking the data section 33 dot, and then we can square it. And so that will result in a new Y matrix where each of the values here have been squared, as you see. If you wanted to operate on data in different files, each having a different file name, then we have to employ a different technique. So here the user will enter the file name when requested to do so, and as before, the script will square the data residing in the file whose name is specified when the script is executed. So take a look at this code here. I'm going to explain in a second what each of those means. But so we have file name 1 equals, there's our input function again. So we're prompting the user to enter a file name, including the suffix. Again, we use this here to signify to MATLAB that we're going to be taking a string as an input. So whatever the user enters, that's now going to be assigned as file name 1. And then when we load, we can load that file name 1. So it's basically just going to input that value here. And then we have m is equal find string file name 1. And then I'll explain here in a second what the rest of this means. So find string locates the position of the first occurrence in the string of characters within those single quotation marks. In this case, just the period that was in the single quotation marks, like you saw here. So we're finding the string that is up to, so we have this m-1 that is up to but not including the period in file name 1. So you can see that here. So it's finding the string up to but not including the dot from file name 1. And then since file name 1 is still unknown to the remaining expressions in the script, it must then be converted to a numerical quantity. And this is where that eval function comes in. So that evaluates the string quantity appearing in the argument. So that's what's going on here. It's evaluating that. And then we have our y equals data 1. So now that's been reassigned as data 1, and then we've squared that data. Saving files, to do that, you're just going to use the save command. So we have save your file name, and then you can save however many variables. And then this here is your format. So in this case, we did the ASCII. ASCII is a string indicating that the data will be saved in ASCII format. So let's look at an example here. So let's say that we load a file, that data section 33 again, and we're going to manipulate it to where we square each of those values within that text file. We can then save it directly from the command window, but this time, so we say saved data section 33, so that's what we're naming the file this time, and then the variables that we're saving, and then that ASCII format. And then when you execute the code, this will be the new matrix or the new data set that you have contained in this saved data section 33. When just the file name is given, MATLAB places the file in the current directory. However, if you want to save it to a different directory, then you have to specify the file path for MATLAB. So again, let's say that we load that data section 33, we do y is equal to where each of those values are squared. In this case, for z, we do the square root of each of those values, and then we save it, but we don't want to save it just to the current directory. We want to save it in this particular directory here. So you have to specifically identify the path for MATLAB first, then you specify your variables, again, your ASCII format, and when it saves that saved data section 331, we now have this larger matrix that contains the values for y and z. So these were the squared values, these were the square rooted values. Cell arrays. First let me say that pretty much summed up the strings and how you create them and manipulate them. Now we're going to talk about cell arrays. And cell arrays are a special class of arrays whose elements consist of cells that themselves contain arrays. So they provide a hierarchical way of storing dissimilar kinds of data, and any cell in a cell array can be accessed through matrix indexing, as was done through standard notation with the vectors and matrices. Cell notation differs from standard matrix notation, though, in that open braces and closed braces are used instead of open and closed square brackets. So let's look at an example here. We're going to create 4 different arrays of data as shown in the script here. So we have A, B, C, and D. Okay? When you execute the script, that's going to result in A, B, C, and D. So we can see here this was just a ones of 3 rows, 2 columns, magic 3, so that just created the random 3x3 matrix for us. We used that char or character function, so that created a string matrix that has pressure, temperature, and displacement, and then D was just equal to this complex number here, and then a scalar. So again, when we executed it, now we have these 4 different values here for these matrices. And let's say that we now wanted to add to this script the cell assignment statements to create a 2x2 cell array, which is analogous to that used for standard arrays, except that we use braces as delimiters. So in this particular case, we have our 4 matrices that we created again, and then cell. And then notice the curly braces here is A, B, C, D. Semicolon was used to create the 2x2 matrix. So now cell, when you execute it, is telling you the size and the type. So this, we have our A, B, C, and D. So you can see these are our 4 different matrices here. But again, it doesn't tell us the specific values. It just tells us the size and the type for each of the matrices. If we wanted to display specifically what is in each of those cells and not just the size or the data type, then we could use this cell display function here. So now we've created cell. So again, we've got the curly brackets, but this time we're using the cell display of cell. And so when we do that, now it's telling us cell 1,1 is equal to A, cell 2,1 is equal to the string matrix that we created, cell 1,2 was equal to our magic 3 matrix, and then cell 2,2 was that complex and scalar matrix that we created. And let's say that we wanted to access each of the cells individually. We can do that as well. So in this case, again, so we have our 4 matrices. We have our cell, so we're creating that cell that is comprised of all 4 of those matrices, the 2x2 cell. And then in this particular case, cell 1,2, we want to access that one individually. So this would be the syntax cell, and then you can use that curly brace with the 1,2 to indicate that you wanted to access that magic 3 cell. With cell arrays, we can also use the sort function, and that's going to ascend those in dictionary orders or in alphabetical order. So let's consider the following script. Let's say we have words and then it contains strings, the application, apple, friend, apply, and fiend. If we use the sort command of words, and then notice this prime notation here, so we're transposing it to make it a column vector, and so then what that's going to do is it's now sorted all of those words in dictionary order for us. All right, so last topic here, we can input Microsoft Excel files directly into MATLAB, which is really convenient. So to do that, we use this function here. So the x comma y equals XLS read, and then your file name, so that does need to be in the single quotation marks. So X will be an array containing the columns and rows of data, and Y will be a cell array containing any text headers that accompany the data. And then of course your file name must contain the suffix .xls because that's what's indicative of an Excel file. So here's an example here. Let's say that we wanted to load an Excel file that is force display data that's comprised of these values here. So we have KPA, we have millimeters for our displacement. So again, these are going to be our X values and these are going to be our Y values. So when it loads that into MATLAB, it extracts each of those the numerical values for our X, and then our Y is comprised of a 3x2 cell array, where cell 1, 1 is this transducer linearity. So 3x2, so we can see that we have 1, 2, 3 that contain text by 2 columns. So hopefully that makes sense there. And that pretty much sums it up. The last slides here contain some example problems that you should try. The code is a little bit lengthy compared to what we've seen. However, these are good problems for you to try yourself. You know, don't just copy the code in here. Just give it your best shot. But like as usual, we have provided it here. Particularly what I want you to notice is that this example here contains a for loop, which we haven't discussed yet. That's going to be discussed in the next chapter. But go ahead and start familiarizing yourself with this just so you can kind of get a feel for what we're going to be discussing in the next video. And then here's a second example here. Again, you know, give this one a try, see if you can derive the solutions for that. And then here's a couple of textbook examples that have been provided for you that make use of the display, the FPrintF, RepMat, we discussed that before, and then also using the num to string, and then FPrintF display into string. So these are some good problems so that you can practice some of the topics that we talked about today. As usual, if you have any questions, let me know. I'll be happy to provide additional notes or videos or anything that you guys need, so just let me know. Thanks. Bye.